Pleased to have Jakob Zeitler from Oxford telling us about his work. Great, yeah.
Okay, well, thanks for your time today. I've prepared some slides on something I've been working on for the last 12 months, roughly. And it's very much in line with the Newton course theme, which is a question at the interface of theory and practice. And so I'm going to talk about adoption challenges for partial identification. So I'm Jacob. I'm currently a postdoc at Oxford University in the statistics department with Robin Evans. And I'm also part of Smart Biomed, which is a center between Oxford and Danish universities. I think Erin Gabriel is part of that as well, who's also somewhere around here today, or in the program. Okay, so I prepared a 5-course menu today. Some of you have started with the start already. But we're going to talk first about what partial identification is, so we're all on the same page. There's people online as well, so we're going to do that for those. So we'll all know what it is. Then we're going to talk about where does adoption fail. So some observations there. Why does adoption fail, and then what we can do about that, and some predictions. Feel free to ask any questions in between. This is an interactive talk, not a lecture, I hope. So yeah, any questions before we start? Good, right. So first we start with a survey. So if you open your phones, I'd really appreciate if you scan this code here. And so as we are on average statisticians, let me also close my overleaf behind here. I'm interested to learn first, where people come from, so I can tailor this talk a little bit. So if you get a subsample of the room, that'd be great. I think the answers will appear here on the screen.
What do you mean by what kind of causal inference do you do?
It's very open-ended.
I'm just saying graphs.
Yeah, you can say graphs, you can say IVs, you can say actual causality, which is also a thing.
You can enter more than one word.
Yeah. You can be as specific as you want. You can say you're really into... No, that's fair. I think actual is a good word. I want to talk to that person. General causal inference. Okay, I guess that I wouldn't. Discovery. Partial ID for hard decisions problems. Single worlds. Graphs. So that means 3 people might have put in graphs, I think, or 2 people. Okay. Design-based. The best kind. Let's go to, I hope so. Discovery, got another hit. The worst kind. Okay, well, that's what my talk is about. No, so that's great. So there's another question after this. So have you heard of causal bounds before, partial identification? So either everyone clicked yes. Okay. Oh, you're right. So yeah, so we got actually 14 people logged in. That's nice. Okay, that's good actually. Yes.
Is this free actually? Because I'm curious if I can use for teaching actually.
I have. So what will happen is you will ask your university administration, and then they'll probably already have one signed up. This is the free one, which I like more. Oxford does not use this, but this is the better one. But it's limited to like 3 questions, I think. That's why I have 2 surveys. Okay, so that's good. So most of you have heard of it before, so we're going to be a little bit faster on the introduction then. Yeah, this survey, I used the same survey that I used for people in another talk on partial identification before. So they're more applied. For them, things are scary. So, but maybe for you, still things are scary. So you can share that. Maybe you're really afraid of faithfulness. Hope people don't. Oh yeah, no, you can be afraid of that. I'm afraid of that. Complicated notation when someone uses X and Y and L and U and Z. No, this is good actually. Good, great. So I think that was, please use my Okay, we'll move on. Right, so thanks so much. So most of you know causal inference. You all have some fears that are valid. and you work in all kinds of ranges of causal inference. So today I'm talking about partial identification in this first section, just so we're all on the same page. Again, 87% of you have heard of this before, but I'm going to provide my introduction to that. I did my PhD in this, I wrote my thesis on this, so I have some thoughts to share on this, and this is how I would introduce partial identification. So here's an example where we had a clinical trial in 1984, and that has been used, that data set, in a paper by Alexander Bauke and Julia Pearl, which most of you, I assume, have heard about. And so in this paper, Pearl and Bauke looked at imperfect compliance. So just because you have a trial doesn't mean you immediately can calculate the effect, because you might have imperfect compliance or non-compliance. How does that look like? So if your research question is, what's the impact of cholesterol lowering in reducing the risk of coronary heart disease, then you might be looking at a graph structure or the IV structure here on the left when you have non-compliance. So non-compliance meaning that when we have a prescription by the doctor, actually taking the treatment is still an open question. So some patients might not take it, and that might be due to factors such as age or gender and so forth, and those might be unmeasured. So it's pretty standard. What we then can do is we can, collect some data on that. This is the original table from the paper, and what we get is bounds. So what are bounds conceptually? Here we see them at the top. So the average causal effect of D onto Y, so like the actual treatment. So when people do cholesterol lowering on heart disease, that we can bound with these methods here. So we see 0.2 is the lower bound and 0.8 is the upper bound. And so this means it's actually informative. So we're not including 0 here. So we know that it's definitely always going to be above 0. The equation you see down here is derived in the paper. And so this is what someone would call analytical bounding, maybe, because you can inspect these equations and interpret them. And again, I'm not going to go into those because you can see them. But most importantly, these are not confidence intervals. So it's commonly misunderstood, but there's nothing about confidence or alpha or anything here. These bounds, if the assumptions are correct and we have the data, are guaranteed to include the true causal effect. So don't confuse that. Okay. What's the intuition on partial identification? So again, we'll see a few more complicated problems, but what always works well for me personally is this idea of that we have different models that imply different causal effects, but together they apply a range of possible effects. And so here's an example from Hu et al. In 2021, where we again have the IV model. So we have an instrumental variable Z, then we have a treatment A and an outcome B, and some unmeasured confounding U. And we might consider a model 1 and a model 2, and these are the structural equations. So everything here is binary. We're just going to look at binary cases. So in the first model, we can ask the question, okay, what's the probability of B equals 1 given the intervention on A equals 1? And so we can actually read this off the table here. So model 1, so we look at, okay, intervention A equals 1, that's this one here, and then B equals 1, that's this one here, this one here. Okay, well, we can conclude in all cases it's going to be 1, so the probability is 1 or 100%. Then if we look at the probability of B equals 1 given the intervention A equals 0, we do the same thing. So B equals 1 is here, here, and then A equals 0. Well, we have none. Okay, so it's 0, right? I almost confused myself there. And so the average causal effect is then just the difference between the two, which 1 minus 0 is 1. So the model 1 implies that that would be a possible causal effect. In model 2, we have a similar structural equation, but a change here. So in this model, if it was true, we could do the same exercise, but we see here when we say B equals 1 given do A equals 1, so that's only this row down here, we see that depends on whether U is equals 1 or not. And so we can say that the probability of U, this unmeasured confound equals 1, is just defined as P. And so therefore we can conclude that, okay, well, this is going to be probability P. It's unobserved, but that is what it would be. And so in this case, the average cause effect would be P minus 0, so that's P. What does that mean? So if we have two structural equations on B, two possible models, and we cannot reject either of those, that means that when we take the worst cause effect and the best or the highest and the lowest cause effect, they basically constitute the bounds on a range of cause effects. Does that make sense as an intuition level thing? Okay, we'll come back to that later a little bit. Okay, so yeah, go ahead.
You're confused. You're referencing that paper, the bounds can be worked out mathematically.
Yes. Yeah, yeah.
What is this paper adding?
So this paper is on the recent literature on continuous bounding. And so they use this example to motivate or give some intuition. So like a machine learning approach, as I'll show later, would consider a set of models, then reject those that don't fit the data, and then calculate the effects for those, and then the lower and upper bound would be the bounds for that. I'll show one example later, but yeah, so I'm just referencing it because I like that example. But this example, I think, has been used elsewhere before. But of course, we have analytical bounds that you can derive from equations, and then we can also take a more, let's say, data-driven approach, which is what I just showed you in the example. Okay, so identifiability, that's the game you're playing here for 6 months, really, apart from structural equations, I guess, structural learning. And so the question is, can we express the effect of interest from data? You can say yes if you make certain assumptions, and then you say no if your assumptions are not enough to identify that. And so I'm showing that here because for most applied statisticians or causal inference people, this is their world. They're like, okay, I go into my epidemiology course, what are the 3 assumptions I need? And then, as soon as I check, have these assumptions, I now got my point identification. But there is a world in between, which is partial identification. And so when people say it's not identifiable, it might be partially identifiable. So this is kind of like the decision tree we could look at. And so, for example, maybe you don't have confidence in your strong assumption that there's no unmeasured confounding. Okay, maybe partial identification might be a way to get some causal results. Traditionally, then also partial identification might be put into sensitivity analysis if that resonates with some people more. But again, these are just different conceptual introductions. Okay, not too bad. So that sounds cool, right? So partial identification gives you bounds. These bounds come from assumptions that are weaker than full identification. For full identification, I personally think you need a really heavy machinery to get that single point. Well, we can just tone that down to like lightweight machinery, lightweight assumptions, and then you get bounds, right? So that seems like maybe a more conservative, less risky play or something like that. So do people do that? Have you published any papers with bounds before? Raise your hand. Okay, so some people do it. Now, here's the best example I have to just kind of like showcase that most people don't, is that, so Luca and Mats and Aaron did a review paper. Is Mats still around? Probably not here today. But they looked at 309 papers, specifically in the context of instrumental web analysis, and not a single one of those reported bounds, even though bounds for these kind of like methods are actually readily available and easy to calculate. So that's kind of a problem from a statistical perspective, because we want to provide a comprehensive, result and analysis on the question at hand, but people don't do bounds, right? Okay. So any objection to that? Okay. Yes.
I think people make bounds implicitly, right? They might not do a formal sensitivity analysis of formal bounds, but they think, many of these studies I expect when the results are interpreted, people will think about like the degree to which there are problems, and then kind of impose bounds in their minds.
Impose? Well, yes, but I guess my point is like I would love to see them published, if that makes sense. Yeah, okay. So 10 months ago, I then asked the question, why? Why does this happen? Like I spent so many years of my PhD developing these really cool methods we'll see too later, but like no one's using it. Why could that be the case? And so I went on a journey. And so the first decision I made is that what I think doesn't really matter, because I think we all have our different opinions and come from very different, trainings and levels and so forth. So I need to get an idea of what people think, what other people think that have worked in this. And so I had the chance to talk to at least 20 researchers, and many of those have published papers in bounds, and this is still ongoing. But some interesting things here. So number one is that lots of them say bounds often seem, in the very large majority of cases, to be right, to be useful. That's an interesting answer. And then others are saying, you know, I have written multiple articles on these things and questions that you raise. So they're also on the same path that I'm exploring here. And so what was very interesting is that, yes, go ahead.
I'm just wondering, I don't know if you have it on another slide, but how did you word the question about?
Yeah, so.
Oh, okay.
Yeah.
Okay.
Yeah.
So what happened for me intuitively is that the kind of distribution emerged in my mind of like different opinions. You know, there was like people who still very much cared about it, and then other people who were like, I don't care about it because it's white. And then the middle who was like, heard of it, used it, but don't have a strong opinion. And then also, if you look at how people publish on bounds, there's an interesting thing where some people use bounds in 1 or 2 publications and then never again. So why is that, right? So these are the survey questions I put together. I'm not a survey design expert, so this is probably really bad. But I just went with it, copy and paste. I would send it to people on email or show it to them on my screen. Being here a month ago almost 2 months ago in Newton, I also had a few conversations, I think, with some of you. And so went through these questions. Long story short, it was like, number one, do you use bounds? And if you had to explain it to someone, how would you explain it to them? What's the killer app? You know, how would you show them a good example? And then if you would agree that people don't use bounds enough, what are the barriers? And then finally, is there any other comments? But yeah.
Do you have a sense of when people, how do people interpret bounds? Like, do they interpret it as partial identification in the statistical sense or sensitivity analysis? Because these two bounds are centered on completely opposite sides of the spectrum. So when people say like, oh, the bounds are too wide, they're probably thinking about Mansky bounds, like Balka-Pro bounds, versus like in principle, sensitivity analysis can be as narrow as you want it to be.
Yeah, good point. We'll get to that too. This is a great audience. So we'll get to it. But long story short, both. Yes. So you're right. So some people think of this in terms of sensitivity analysis and then adding more constraints and assumptions and so forth to make it tighter. But others have just stagnated with, maybe that's not fair, but have decided that, oh, these bounds are like this. No, I'm just going to keep on doing full identification. This is the problem we're facing, essentially. Like, why do we have these different approaches or these different like mindsets? But both of them appeared. I think it's probably some 50-50 split. And so from these conversations emerged maybe 2 types of adoption failures. So the first one I call barriers. So barriers have different heights, but you can overcome them. So you can just throw money at it, you know? So one of them might be software. So if you do bounds right now, like the most simple bounds, maybe an IV model, they might be by default available in your R package for instrumental variable analysis. It's literally just one run or call, and it gives it for you for odds ratios on all these kind of things. But then there are some things like, oh, I don't actually want to do discretized data. I have continuous data. Or my model is a bit more complex than just an IV model. And this is where we don't have software right now. So, but you know, if we had the money, we could pay some people, or ChatGPT, and then it would build all the software for us. So that's like a barrier, right? That can be lowered with money. But then the question that was much more important for me is like fundamental limitations. Even if I can give you the software and it's like Siri and you're like, please calculate bounds, and then Siri gives you the bounds, would you still actually use them? And so these are like 2 questions of like, well, do we have actually a value of analysis for the practitioner? And then also like, do we have a lack of killer apps, right? Yes, go ahead.
And I think to just add that, I mean, implementing software is one thing, but it's like, is it also possible to run before the heat death of the universe?
Fair enough.
It's like,
Yeah.
So, yeah.
So this is where I would be like, so barriers, the action point is you need to ask, is it worth the investment? And I guess we're not gonna, you know, the paperclip argument, we're not gonna like invest all our atoms and energy into calculating bounds. Probably not, right? So there's a limit on that. But then I think when you are like, okay, well, we're not gonna do this, then, you know, it seems like there's nothing you can do, right? So, or it is not worth the investment. So that's correct. I think that's part of that too. The heat of the universe, great. So here's some practical barriers. Number one, discretization, right? So like bounds traditionally only work in like in a binary setting or categorical. Again, if you have used bounds, you know what I mean. And then also exponential growth in parameters, number and variables. This is what you mentioned essentially. And so those are technical challenges, and this is kind of what I spend my time on in my PhD. So there's something called approximate partial identification, which basically uses that intuition that I just showed before. So you define a class of models, you reject those that don't fit the data, you calculate the average treatment effect for all of those, and the highest and the lowest, well, these are your bounds, right? It's approximate. We don't have guarantees. It's a non-convex problem. But what you see here is that, even for high-dimensional treatments and a high-dimensional outcome, you can get bounds on the true effect. This is the data density here. You see where we have high density of data, we get nice bounds, and where there's no data, the bounds are wide. Like it's a cool method, but there's no software to use this right now. And running these bounds took like server clusters and stuff like that. So again, could we throw hundreds of thousands of dollars at this and give you a single R line? Yes, but should we invest this money? Then for the second question of like, okay, well, the heat depth of the universe. So one trade-off is something called the causal marginal polytope. So in the partial identification formulation, we have usually parameters that grow exponentially as you have a bigger graph or more domain space. And so what we can do is we can look at just marginals as basically a trade-off between the width of the bounds and being able to calculate bounds. And so yeah, so that's what I've done here. So it can be solved. Barriers can be lowered. You can pay me a PhD salary and I'll work in it and bring those down. Then you could also pay someone a software development salary and they might build a nice software. But the limitations is kind of like where it starts to become problematic. So uninformative bounds means that you include the zero, which basically means you can't really conclude with those bounds whether the effect is going to be positive or negative. And so this is what I call the uninformative objection. So this came up a few times in the surveys, and people were like, well, that's great, but bounds are too wide. And this is not a complete story, because I think it's somewhat of a clash of like cultures and perspectives and incentives, right? Because you have the statistician who's like, well, but in theory, we can calculate these. I could spend some more time deriving more bounds. I can give you approximate bounds if you give me some more money to pay someone to build the software and service. But then you have the decision maker who's like, that's great, but I still need informative bounds as a minimum. And ideally, I want that single number to give to people. And those are the problems that usually people in applied stats face. And so I put this together yesterday as kind of like a show of the landscape. But what we have basically is that like as a minimum, we're always going to have some data. And then we can like make the minimum amount of assumptions. If you don't have an IV, this is a rough guide. If you don't have an instrumental variable, usually if you take data and minimal assumptions, you're not going to get an informative bound. Sometimes if you have an IV and you have IV assumptions, then you get bounds that exclude zero. This is what we saw in the motivating example at the very beginning. So where you lower cholesterol and we don't get a point identification, but we can show provably that it will improve your heart disease risk. And then of course on the right side is where most people spend most of the time, which is like point identification. And so you have full identification assumptions like no unmeasured confounding and overlap and so forth. So here are some quotes. So someone responded, the problem actually is that people think he said deterministic bounds are too conservative. So this is essentially what you mentioned here, which is like, actually no, in sensitivity analysis, we can just add more constraints and add one parameter to like, suggest our idea and play around with it until it excludes zero. And then at that point, we interpret this, modeling decision, and then we're like, under these assumptions with this parameter set at this value, we're gonna get informative bounds. But then also like, these are my comments on the left and right. I personally think that like, just doing a bounds analysis is incomplete, right? Because why don't you do just a bounds analysis plus full identification? Obviously, I spent most of my PhD on the left side, so I was like, oh, maybe I should also do full identifications for the examples that I work on. But then, of course, we have people on the right side who are also like, now I'm just going to do a point identification and then we're done. And so, but down below is essentially like the playground, right? The statistician, in principle, would be happy to play with all of this. I have my data and I have a different range of assumptions. But then the decision maker, they just want to play on the right here. So why is that? So Charles Mansky wrote a little bit about this, actually not a little bit, a lot about this. And he summarized it in 2019 with a paper on the lure of incredible certitude. Has anyone seen this paper before? Great. So it's a eye-opening paper for me personally, and essentially, like, he mentions a whole bunch of things, psychological, sociological factors. For example, he's like, okay, you know, building trust. If scientists want people to trust what we say we know, we should be upfront about what we don't know. Makes sense, maybe, right? But the problem is the decision maker doesn't maybe have the time. They don't have the incentives, right? He also actually interestingly summarizes, study of partial identification generates strong reactions. Many scientists hold firm to the traditional practice of reporting point estimates and predictions, even though they may rest on fragile foundations or have obscure interpretations. Which is kind of my experience, right? Because I'm like, use bounds, the bounds are cool, you know, it's an interesting analysis and so forth. And then he also has a quote here from Jerry Hausman, who was like, you can't give the client a bound, the client needs a point. So this is the true reality of practice, you know, like if you think of causal inference and using causal inference in practice, very down the line at the hardcore decision-making level, you're gonna have these opinions. So, yeah.
Question about the last quote from Hausman. If we give confidence intervals all the time, you know, client seems usually happy with that.
Yeah.
So why did they say we can't give client a bound?
It's a good point. I don't know. Clearly, this quote is somewhat out of context, so there might be more to this. From my experience, I think, yeah, we give confidence intervals, but I think people still ignore them, a lot of them. I don't know, people know how to interpret confidence intervals, but you know, I mean, that's probably a separate study.
I thought part of our kind of job was to educate people about uncertainty. This is why I felt the way you said not covering zero means non-informative is quite an interesting choice of word, because you still get a bound and it contains some information.
Yes.
It doesn't contain like immediate action, perhaps, that like unequivocal action, but
No, I fully agree.
somehow people think about kind of containing zero or not being able to reject null hypothesis means no information was like this is useless. That's pretty problematic.
So this is the response you'll get from the average practitioner who has to make a recommendation or suggestion. I agree that a bound that includes zero still is informative because it includes a certain space of the possible effects. But I think the task of a statistician in some ways, again, to highlight all the different assumptions, right, that lead to all kinds of different results and justify and characterize and, be skeptic about the results that come from them when we increase the strength. But the applied person, they just don't think of that. They barely, most people don't know about bounds in the applied setting. How would they even be able to consider that they should be doing bounds, if that makes sense? So I agree with you. It's just the reality is that people don't care, but there's some reasons we'll get to.
Yeah, great. Yes.
So, do you think that it's really about points versus bounds? I would say that it's more kind of decision makers or clients or whatever that don't like the answer. It's complicated. So I can give you many point identified on a different set of assumptions.
Yes, yeah.
And I don't think that people will be happy with 10 different point identified answers, right?
I agree.
Because then the answer again is complicated.
Yeah, I fully agree. I think if we don't do bounds, let's at least do what you just said. But I don't see that much as well. I know some people do, and it's great, but we'll get to the factors behind this. I think it's definitely worth mentioning that even there it lacks. So actually, Michael Jordan came to Oxford to give a talk. Michael Jordan, people know Michael Jordan, Berkeley. Yeah, yeah, it was great. And he actually gave a talk. So he's moved to Paris, and he's dedicated that time in Paris now to the intersection of statistics and economics, and specifically kind of, I'm going to say, incentive theory. And so do incentives drive the world, ? Right? Because how can we explain behavior such as people not using bounds? And so that maybe works in the concept of incentive theory. And so here's another quote from Mansky's work. More than once has it happened that congressional appropriations were endangered when it was suspected that government statistics might not be 100% accurate. So this is a quote from 1963, and of course statisticians are trying to do the best science and data analysis to inform decision making usually. But on the other side, sometimes expectations can be very high, and of course that word accurate does a lot of work here, right? What is an accurate statistics? I mean, I wouldn't agree with most people on that anyway. But so long story short, I think that we need to use incentives to drive the adoption of bounds, the same way Michael Jordan is using incentives to drive the adoption of better, efficient marketplaces for all kinds of, economic questions. He's mentioned, for example, like incentive theory is used to coordinate organ donations, and that makes sense to make that work well, right? So why shouldn't we use incentive theory to create better causal inference adoption? So that comes to my call for action. So I call it like the partial identification roadmap. And so there's like 3 things that emerged from the surveys. Again, I'd like to think myself of here as being the vessel of people's opinions. So I'm just trying to summarize these things. These aren't necessarily mine opinions. I'm just trying to summarize what comes out of the surveys. And so 3 things came out that stood out. So number 1 was people were like, well, let's just talk to them and tell them what they should be doing. The other one is like, okay, well, you want to lead by example, right? You need to show people how it's done. If you just tell them do bounds and you don't give them an example, like how they're gonna understand. And then finally, it's like you need to change incentives. So the first one here, Charles Mansky has a quote. And he says, this is, I think, actually at the end of his paper, I conclude that researchers should generally strive to convey uncertainty clearly, which is, I think, was mentioned here before as well. And I agree, right? They should. Bounds would help with that conveying of uncertainty. But I would say yes, but incentives apparently don't support that. So that means we need to create incentives so people change their behavior. So what about killer apps, right? So presumably there should be some examples that if someone comes around, they're like, hey, I've heard about bounds. Do you have an example? I should be able to like just pull up my phone and be like, here's a paper, read it, and then use the software if it's built. And there are actually some interesting things to consider. Number 1 is if you use bounds just to supplement results from full identification, people probably won't care because they already have the point identification. That is the recommendation, medical statistics or policy or politics, whatever. But they're going to be like, well, the bounds, they don't change my opinion. So what we need is probably applications of bounds where using the bounds in some way has changed the outcome or the results if we only use point identification. So does that make sense? So you need to show the value of using bounds, where when you use bounds or partial identification in your analysis, it actually changed the result in a significant way such that everyone else now should also be using bounds. So they can, protect themselves from a wrong analysis. And so Charles Mansky has written some papers on this, which I list here. But does that make sense?
Yes, sort of, but I guess if you have bounds, then those will typically contain the point identified value, right? So the possible ways that it can differ from the conclusion from the point identified estimate is really it can either qualitatively agree with the point identified guy, or it can like contain 0, and that way it like differs qualitatively. But like it's sort of hard to think of how you would have like your bounds are on one side of 0 and your point is on the other.
Yeah.
Right.
I agree. It's work in progress. So this is one of the parts I don't have an answer to. I'm just trying to bring together basically the factual reality you just described and the fact that people aren't going to change the way they do things if you don't show them that this could materially change the outcome and the results. So I do think that there might be examples like that. I have some notes that I still need to go through. But that is a problem, right? And so this, again, now let's think about it. Is this a barrier where I throw money at it and then it gets solved? Or is this actually a fundamental limitation, right? Because if it's a fundamental limitation, we won't find enough examples of the kind that you just described, then we're going to have a problem with adoption.
Yeah, maybe a compelling story, hypothetical story, right, could be that you see you do a point identification, you have beneficial effect, but the assumptions are sort of clearly unreasonable and your bounds contain 0, and maybe you do a subsequent experiment and you see in fact this is harmful, or a policy is rolled out and you see that it's harmful. That would be like a pretty stark example, but you'd have, I guess, you'd sort of have to get lucky to find something like this, right?
Yeah, and I think the chance is non-zero that this exists. The question is, how much does this exist for other people? Because if this is 1 out of 10 cases or 1 out of 10,000, stats papers, are people gonna really do extra bounds because of the one case where someone had bounds and they changed their opinion? I think they should, of course, but it's easy for me to say as a statistician, right? And again, it comes down to well, then just do the bounds, and they're like, well, how do I do it? And I'm like, just implement the algorithm. They're like, I will not, because statisticians right now don't have the money to implement these algorithms, if that makes sense. Okay, 2 questions, yes?
Well, it's very much related to that. The whole motivation for going for bounds presumably is that you're going to pay a price. If you instead opt for making stronger assumptions just because you don't know what else to do, and then get point identification, and the price should be that you're often going to be wrong. Right? And that's a real price, because it might mean you're going to put all kinds of drugs in the market, and after many years you find out, oh no, it's not all working as well as we thought. So if there aren't such cases to be found, that seems very strange. There have to be, right? The whole theory is pointing to that conclusion. So that's what I would imagine to be something that we should focus on.
I agree, and I think that's maybe part of the one things that I mentioned, is that we should actually go and measure that damage or that price, right? And then you can take that to decision makers and be like, you should do better science, because you're actually losing out of these. You in the best case losing on benefits, in the worst case you're making destructive decisions. I agree.
And in particular, you could have, at one point you have put identification, and then many years later you get much better data, and so now you get a different point identification, and it's a wide gap, and a statistician could come along and say, I could have told you all along that both of these are still within the bounds that I have given you initially.
Yeah, I see that. Yeah.
I think there's more complexity to decision makers' incentives, but I agree that is something we should link it into. Who's gonna make that point? So yeah.
Kind of along the lines about who pays the price. I feel like you're talking about the carrot, but your discussion also highlights the current stick, or the disincentive. So researchers could also be concerned that if they use bounds, they overturn the results of their own study that they're trying to submit. And if they're kind of just applied researchers, they're not FDA, they're not clinical trial people per se, they're not trying to get a new drug to market, there's not so much of a cost right now for just effect estimates.
Yeah.
It would be really interesting to try to run an RCT where you submit the same empirical applied paper, one with bounds and one without, and see how reviewers respond. Because if reviewers don't really understand how to interpret bounds, that's also a reason for the current equilibrium. If they see the bounds are wide and they don't really understand what these wide bounds mean, then that can kind of document why are we at this current equilibrium.
I agree, which comes to my third point, which is the strongest point, which is essentially, so Mansky also said, there kind of really 2 key steps to causal inference or statistics or bounding, which is number 1, determine what can be learned when the data are combined with assumptions that are weak enough to be credible. So that was on the very left of my schema, if you see that, minimal assumptions. And then from there, step 2, explore further, what can be learned with data combined with stronger assumptions. And so that kind of 2-step approach, or any kind of other schema, well, what if we ask reviewers to check whether that exists, right? So one suggestion that has come in some of the survey responses was well, the only way you're going to change behavior is if you start rejecting papers that don't have bounds. Makes sense, right? This is where the things are happening, but I don't actually know if reviewers right now are well equipped, if we have well equipped them to analyze bounds, and so I think maybe that would be a good next step, to write an instruction manual. How do I, gracefully reject a paper that didn't use bounds or something? But yes, so I think that's part of the problem right now. Does that partially answer your question?
Yeah, it might be harder to get people to reject papers, or I don't know. But in execution, maybe there's.
Well, it's also catch-22, right? Because if you reject a paper and you say do bounds, and they're like, yeah, but I'm not going to implement the software for bounds, so I'm going to wait for that. Then we're just going to be in a circle of nothing happening, because everyone points to someone else saying like, oh, I can't do this yet. So I'm speaking from the mindset of a medical statistician on a 1 to 2 year fellowship who needs to publish papers and is not going to learn yet another method, right? It's not going to happen. Yes.
Oh, can I, just coming back to the point of like, I think there was this point raised that the bound will always contain what you obtain through pointed identification. I don't think that's true. I mean, like, you can produce simple examples in simulations where if you leave out an unmeasured confounder, you obtain like point identification for an observed data parameter that's negative, but the bound is positive. So I think there could be interesting examples where the bound actually disagrees on that.
So I have one example in my appendix, but because it disagrees, I'm still wondering whether I made a mistake or not. So I'm like, I have it, I could show it to you, but I won't, because I might be very wrong. So I'm still working through it. But yeah. I'll send it to you by email. You can tell me if I got it wrong. But yes, you were next.
I guess, by the way, thanks for bringing these discussions. I guess one slight objection to this, and by the way, I also do bounds, is that there's this recent paper, I think on JAMA, or don't quote me on the journal, that looks to see whether acetaminophen and Tylenol is harmful during pregnancy because of the whole Trump thing. I remember most of their analysis, not all, was based on point estimates and confidence intervals. And they conclude that Tylenol, by the way, does not cause anything during pregnancy. But I think if you were to take this approach and do it by bounds and narrow it, start with a bound that's wide and narrow it, and then narrow it and still contains we're not certain, I feel like that would have a entirely different scientific implication. So I guess that goes to the broader question of, is it more scientifically useful to have point estimate plus confidence intervals from different angles and interpret those from an applied scientist, rather than having bounds and then narrowing the bounds through further as a way to make progress in science? I feel like not every question should be based on this Mansky approach of doing it, but because it would then lead to certain immediate cases where I think that would be quite harmful, actually.
Yeah.
So I don't know if there should be a black and white, but I think we should think at least more higher level about what type of analysis if they're doing 10-point estimates and then applied scientists interpreting those versus a bound and narrowing it will lead to more better scientific conclusions at the end of the day.
I agree, yeah. I don't think we're going to win anyone over by being black and white. I think, of course, it should encourage all kinds of approach to bounding, but yeah, I mean, I hope this is being picked up by the microphones and recorded, but yeah.
Maybe also building on this, did anyone bring up in the barriers discussion the evidence synthesis aspect, like going beyond the individual papers, but the hierarchy of evidence in medicine, the meta-analysis being, the crown at the top, with all the problems that come along, but how then can these bounds be synthesized in all of the pipelines we have, thinking about Cochrane and all of these guidelines?
It's a good point. It actually didn't come up, even though I did talk to like 3 or 4 medical statisticians that wanted to use bounds and then didn't. But it's a good point. I mean, I agree. Haven't thought that far.
Also for the incentives, if I want my paper to be included in the next big guideline or meta-analysis, then maybe I'm more inclined to report a point estimate, because otherwise they may exclude it, because what are these bounds?
There you go. Yeah, I think that makes sense. Yeah, I can see that. Yeah, good.
So how do we define, or who and how do we define that assumptions that are sufficiently weak to be credible?
Yeah, so in the bounding literature, there's kind of like a minimal set that can be shown that's like the weakest, if that makes sense. So like the standard, the first papers were kind of like the weakest assumptions, and then people have been adding things on top. Although I agree that philosophically maybe you can take this to a bigger question of is this really the weakest? But
yeah, but that's not what it says, right? It doesn't say weakest. It says weak enough to be credible. So I can be an applied researcher and say I assume no unmeasured confounding. Yeah. And this is credible in this.
It is undefined. I agree. Yeah, I agree. Yeah.
Following up on Frederick's question, whether the assumptions are weak enough kind of depends on your problem, right? It's not, maybe one assumption is strong for this study, but it could be okay for another study. Depends on how they're designed.
Yeah, I haven't thought about that way. For me personally, again, I don't think my opinion matters much, but for me personally, I would think that you can do a ranking of strength roughly, but I can see a world where you have two assumptions that aren't really relatable, and you can't really say one is stronger than the other. But I haven't thought about this deep enough. I mean, this is also just one suggestion of how to go about it, right? I don't think making people use bounds hinges on these kind of definitions in the first place. I think, yeah.
Follow up on the one before. I mean, I felt the real problem is we just don't know what to do when the problem is not point identified. There isn't a good number of methods when we're in that kind of scenario, and that limits bounds, but also many other things that. Yeah. Because the entire kind of pipeline is built on the assumption that every study at least gives me some point estimate of something that makes sense, but we just don't know what to do when things might not be identified.
Well, yeah.
I don't know, reason about uncertainty about identifiability.
I think that the question of what to do, that's a decision-making question, right? And so when you think of why do you do causal inference or why you research causal inference, that there's two strands, and there's another paper by Mansky here where he shows, not shows, but describes, that you can just study, of course, causal inference by itself. It's exciting. You can look at IV inequalities. You can relate it to Bellman equations, stuff like that. That's interesting, right, on a theoretical level, and it has connections to physics, and it is intellectually hugely stimulating to characterize under which conditions we can make causal claims. Fully agree. But then there's this whole huge body of people that also want to do causal inference, but not research the methods. They want to use them. They want to come to causal inclusion because they're clearly correlation analysis doesn't cut it anymore. So they need to make decisions, right? So for them, it's all about decision making. And so they want that single point because that's what they're funded for to deliver in the most simple case, if that makes sense. Because they're being funded to make a recommendation. So when you have that uninformative bound that includes 0, it's going to be really hard to make a recommendation. So it's always going to be bound plus point identification. I think it's just people shortcut it to, well, if my bound already includes the full identification point, why should I waste all that time on a bound? Waste all that time on a bound. Statistically wrong, not comprehensive, incomplete analysis, but that's the reality. That's the practice. Yes?
I think it's related to this. I think it might also be worth pushing back a little on this picture of the decision maker that you're giving too, because I think there's a lot of we're sort of assuming we know what the decision maker wants, and that somehow things that include 0 are useless to them. But in a lot of if I think back to kind of old school decision theory, where you have a table of different actions you could take in different states of the world, and you do minimax, or you do Bayesian expected utility kind of calculations or cost benefit analysis. A lot of the times they're comparing things that are basically worst case scenarios, and that really actually do even if things include 0, it's sort of how far below 0 can it go, or how far above 0 can it get, will end up being important for making the decision, because it sort of says, I don't know, how high do I have to build this physical barrier against the ocean to prevent flooding? It sort of tells, maybe it'll never flood, but there's the worst case of how much it might flood, and people will use that in cost benefit analysis. And so I think that it might help to couple a little bit more tightly with actual decisions, that are not, I don't think decisions are really made on point estimates that much, actually.
I agree. It's correct that I haven't properly characterized decision makers, didn't even properly define it. What I have in mind is the people that I met in the surveys, which are people that genuinely want to do good statistics, but they're like, I would love to do your bounding thing. Where do I start? And I'm like, I don't have a good example for you, and so forth. And so for them, it's like, well, I need to move on. I can't wait a year to adopt all of these methods, because the payoff, I guess, incentive theory, the payoff isn't high enough or something like that. But yes, I think there's probably more that can be looked into. There was a question here.
I think she was next.
Okay. I think building on the point of Dan, I think it's also good to somehow shift the burden of taking this decision from statisticians to the decision maker itself. Because sometimes I think I have the impression that when we give a point estimate, somehow we're saying, okay, this is working in any case, and decision makers often they don't have the sensibility to understand where the assumption fails, where the assumption fails. So
Yes.
I think it's good to, as you said, if we can maybe push to actually get point estimate plus most of the cases, especially when the decisions somehow are really important, involving like harm on people or like this kind of situation where you give the full picture. You say if you are not willing to take this assumption, or if you want to be, as you said, conservative, maybe it's good to take the bound and consider like the worst case scenarios just to be safe, because like people are involved to see this, etc. So I think this could be a good perspective. I'm thinking more like from also the legal perspective, where I mean here there is a measure from fund, but in legal where we're trying to understand what is the cause of an effect is partially identified to that we don't know counterfactual, we will never know what the joint distribution of counterfactual is, but we do have to take a decision. And I think nowadays in court there is the impression that the decision needs to be taken by the expert witness that is going to say, look, this happens due to these reasons, I'm quite certain about this. But the reality is not like that. So often the reality is uncertain. So I mean, as statistician, the responsibility is actually also be able to communicate how uncertain on some of these questions we are. We don't know the answers, we just can't bound the answer, that somebody else needs to take also the responsibility of taking a decision based on this answer.
Yeah.
And responsibility is the key word, of course, because responsibility implies there's an incentive structure. And if you don't want to be blamed for, wrong recommendation, then there's no incentive for you to make that statement. So yeah, I agree. Yes.
Oh, thank you for doing this. Very interesting. I actually think I have very limited experience, of course, but I don't think you are mischaracterizing decision makers necessarily. So at least the doctors or like the small, like local policy decisions that I've interacted with. I don't know. I don't believe it's so much about point estimate against no point estimate. It's more about, do I change what I do or not? And I think, and almost I would disagree with the idea of they are okay with confidence intervals, because in medicine, confidence intervals are misinterpreted all the time, in the sense, if you have zero confidence interval, for me it means no action, no new action, I stick with what I'm doing. Like, I think there is this idea of every single paper should say if I make an act, change what I'm doing, or I stick with what I'm doing. Wait, I'm not saying this right, but I think it is the reality in a way, or at least my reality in a way. But there is something, so at the beginning you said this is very related to sensitivity analysis. And I think sensitivity analysis, for historical and other reasons, are instead widely accepted in medicine, in the sense I've rarely seen an epidemiology or medical paper without any sensitivity analysis at all. And I think we have also a killer example, which is the famous paper on, from Cornfield in 1959, I'm not sure. Yeah, on like smoking, and that's like a good example of people were discussing a lot about point estimates, but then when given the sensitivity analysis, then they got quite convinced that smoking is not a bad idea. So maybe the focus shouldn't be why we like contrasting this partial identification with point estimate, but why do people are more comfortable in sensitivity analysis together with instead of a partial identification all around.
No, it's really good. So first of all, I think a great observation that a lot of decision making is about, should we change the status quo? I think that is a really astute, detailed perspective about the reality and the truth of what decision makers need to do. So I fully agree with that. And then in terms of sensitivity analysis, the reason I exactly mentioned it before, of like you can think of this as sensitivity analysis, is an unanswered question, which is like, should we ship partial identification as a separate thing, or should we ship it as your sensitivity analysis toolbox? Because at the end of the day, right, there's going to be more and more causal inference curricula around the universities in the world. When you have that one lecture in sensitivity analysis, what are you going to spend it on, right? That's a finite amount of time. Should we push for more bounds or not? You know, should we change the status quo from, no, not the Gita and Ben style, you know, actually you should be doing partial identification bounds? Probably not. I mean, these things don't develop strategically and systematically anyway. In a way, the methods that people use, they use because of the incentive structure, because they serve them best for the current incentives. So I think many people hate the Cox model, you know, and they're like, it should have been revised many decades ago. And I'm like, but we're still here, you know, like, so why is that, you know? Yeah.
Just on sensitivity analysis, like doctors use the term sensitivity analysis very loosely, just, you know, change something about the way you've done the data analysis, that's a sensitivity analysis. I think that's fair. But in terms of formal sensitivity analysis, like the E-value is really broken through. Like doctors, I've talked to doctors who have like almost no statistical training and they know what this is. And I think that's because of like, you know, an article in JAMA or whatever it is. So it is possible, you know, for adoption to happen.
Absolutely, yeah. So I think, so I had the chance to talk with Tyler Vanderweel in person about this and have a conversation on this, because the E-value is a good example of how adoption could be driven. He, as far as I know, is personally disappointed with the results. So he expected much bigger adoption of the E-value. So I think we want to definitely learn from those cases. The thing is, the E-value is like, I think,
How long ago was this that you talked to?
over the years, but the first time was 2019.
Okay, I think since then, I think
It might have caught on since, but I have also asked him about bounds, but I don't share at this point what people said, because I think that will create interaction effects we don't need. But he also has shared thoughts about bounding, very short and precise thoughts. Yeah, it might have caught on more now. Fair enough. I'm not up to date what the current usage statistics are. But yeah, I think we should learn from those cases. But the thing is, the E-value is a simple equation, right? Partial identification is not a simple equation. There's a lot of machinery.
I think that has to do with its adoption, is its simplicity.
E-value, yeah, I think that is indeed why Tyler Vanderweel targeted that, used that strategically to be like, okay, we can actually make a difference here. And in a sense, I'm trying to do the same here, you know? I just feel like it's a very different beast. Okay, so this is a meme, we're gonna skip that. So two scenarios I see is the optimist, which is that we're gonna find those killer apps and then we're gonna change minds, demonstrating the value of bounds. We're gonna raise money to make bounding software super easy, you know, or we're gonna convince all the statistical government institutions that there should be a bounding ChatGPT or something like that. And then we're gonna start rejecting papers that don't have bound analysis. Like painting a scenario, right? Whether that's right or wrong, but like this is kind of how it could happen. Then the pessimist scenario is that we find killer apps, maybe, but they're not enough to make convincing cases. So I agree that smoking causes cancer is obviously the killer app for sensitivity analysis, but clearly it's maybe not strong enough yet to make a case for bounds. And so we're not gonna have enough of those killer apps to demonstrate the value, to change their minds. Therefore, we're not gonna find the support to build software, open source, to give to everyone for free. And then we're not gonna change incentives, you know, to have better papers and reject papers that don't use that really simple R software to get some bounds or something like that. I think these are two scenarios that we can't exclude right now. Anyone want to exclude one of those? Okay. And so the answers we can actually learn from history, I think. So here are the adoption curves for different innovations. This is how I look at it. And you see some things take longer, like the telephone, electricity. Internet was super fast, so on the x-axis we have time. And then on the y-axis we have the percentage of adoption. And I think what we all can agree is that causal inference is definitely in vogue right now. So, I mean, the reason there's a 6-month course on this and not 5 years ago is because causal inference is getting more adoption, and we have great marketing books like The Book of Why, which create a whole bunch of buzz and interest and so forth, and the term causal AI, whatever that means. But causal inference is maybe on a kind of adoption curve. It is being taught at universities now much more than before. But where's partial identification? Are we gonna see that curve go up? Because there's something also called the chasm. I don't know if anyone's seen that before. But any innovation or new thing has to go through a chasm phase, which is where it's kind of like make or break. And so I feel like partial identification might be heading towards that right now. So like if we don't find the ways to drive adoption and show people that this really has scientific value, then it might drop off the charts and people are like, it just doesn't cut it. And so, yeah, I'm gonna end with a final survey here. But thank you very much, and I hope this was helpful.